Dr. Smarr.
Mark.
Good morning.
Good to see you again.
Good to see you. Merci.
Here we are again.
I doubt there's anybody here who doesn't know Larry Smarr. I think it's the Smarr and Anderson show these days.
Smarr family.
Yeah, and we have Benjamin
family.
Smarr, we have Joe Smarr. So we're going to have a conversation this morning about the whole idea of flows in computing and who needs it and why. And this started with, Larry and I have this no longer secret favorite thing that we do, which is the Smarr-Anderson road trip. And I have this little silver convertible, and we get into it, and we go places every year. And all we do is just share ideas for about 48 hours. It's the most fun thing I think I do all year long, other than FiRe itself. And this year, so if you picture the little silver car, and there's Larry and there's Mark, and we're driving along. It's very beautiful. It's on an island up in the northwest. And almost from the very beginning, I think we're in the parking lot still, getting onto this ferry, and we start talking about flows, and it just builds. Mm-hmm. And Larry's talking about stories about the increased amount of data in the world, and we're talking about streams of data that are flowing, and how much, and what's going to happen, and who's going to do what about it, and it just immediately becomes clear that we don't have the proper ways of dealing with all that. Mm-hmm. So I think what we're going to try and do this morning is essentially recreate that conversation. And I'm going to ask Larry to give us some examples of the problem and what we have to do to meet it. So would you like to tell a few stories about flows of data?
Well, as you all know, I'm the principal investigator of an NSF grant called the Pacific Research Platform. And what that is realizing that with this exponential increase in big data and big data flows, the ordinary commodity internet isn't going to cut it. And so we really need, like the interstate highway system was needed, as well as Route 66. And so we have been working on this for about 15 years of using optical fibers, which have the ability to carry, 1 trillion bits per second actually in the glass. And to be able to establish between scientific instruments, investigators, supercomputers over the whole West Coast. We take a broad view of the West Coast that goes to Australia and to Chicago, and actually to the Netherlands. It's that New Yorker view of the world. And that essentially we picked scientific teams, and I'm going to give you an example of 2 of them, that typify where we're going over the next few years. And this is hooking up at about 10 to 100 gigabits a second, which is about 1,000 times the speed through the normal internet. So as a person who spent 25 years doing journalistic astrophysics and observation and astronomy, that's close to my heart. So one of them is the large synoptic scale telescope, the LSST, which the NSF is funding. It's a giant telescope being built in Chile, up in the mountains, very top mountains. And it is looking at the sky every night. It reads out about 1.5 billion pixels a second. And it has 2 40 gigabit per second. That's for those of you who have home cable modems that say 10 megabits. Yeah. This is 40,000 megabits a second. 2, the National Center for Supercomputing Applications in Illinois that I founded 30 years ago. It follows most of the observable universe. It in particular follows 30 billion objects in the sky and looks at their changes. So it essentially turns the universe into a video stream. Mm-hmm. And then it's computing anything that moves, gets brighter, dimmer, changes color. How many of those do you think it's going to see a night? Because it has to send an alert out to all the telescopes on Earth and in space. 1 to 10 million. And, by the way, those alerts go out from the telescope through the fiber optics through the supercomputer 1 minute after the observation in Chile. Right. So that's a level of flow that is literally turning the whole universe into a movie.
Mm-hmm.
That's never been done before.
A data stream.
Right.
Yeah, right.
And then in the Large Hadron Collider.
Wait, hold that thought for a minute.
Mm-hmm.
Because we talked in the car that time. Mm-hmm. At that moment when you said that, I pictured what you were saying, and we were talking about visual computing.
Yeah.
And the idea that what's being done there is, it's like slide, and if you see a change, mm-hmm. and instead of having an algorithm, it's almost like you can do the computation literally visually, almost without math, almost without, yeah.
Right. Yeah. You guys think you're seeing the world, right? And there's Benjamin and there's all of these objects in the world. Look, there's just this flow of photons. There's no objects in the photons. And it hits the retina, and there are these rods and cones. Well, these are specialized pattern recognition computers. And they do processing in the eye, which is on stalks, a part of the brain. And then it goes to the back of your head, to the visual cortex. And then there's multiple layers, which are now been abstracted into multi-layer neural nets for deep learning. And it gradually builds up until finally you have cat, right? Because that seems to be the most important object in the universe, according to Facebook updates. Anyway, but my point is, architecturally, already in us, there are specialized pattern recognition computers that are reducing the level of data flow enough that then data products essentially are coming to the visual cortex, where a whole nother layer of completely different kind of processing is occurring. And what comes out of that is your illusion that there are persistent objects in the world that move around, and that's how we as humans work. So we're sort of going through this pattern recognized flow stream every moment of every day.
And it's worse than that, because if you take a kitten, let's go back to the cat thing.
Yeah.
If you take a kitten and you raise a kitten in an environment only of stripes, it can't see bars.
Right. It's a learning system. It's training up.
Yeah, the biocomputer itself becomes designed through early childhood to see what is there. And if there is limited, the perception is limited.
Yeah, it's all about your training sets. It's just like your antibodies in your body. The reason that vaccines work is because they give you something that's a small version of smallpox or whatever, and your body develops antibodies for it and remembers it saw that, and then later in life, if you got actually exposed, it would be able to set up antibodies very quickly. Your whole immune system works that way. That's why, I won't get into it, but the whole microbiome develops the training set that trains your immune system, and you have whatever immune system you have based on what it was trained on, what it saw, what it encountered, right?
So you picture a human being as an organism, and there's this flow of information around it, and the brain is one of the parts of the body that flow hits. It's not the only part.
And remember, this is evolution that's been going on for billions of years, that has ended up saying that's what we need. Now, let me switch.
It's not saying that's everything.
No, but that's what is needed just to survive.
So we're not seeing the world. We're seeing what we need to see.
Yeah. Well, before I get to Large Hadron Collider, just based on, so we're going to do a circle of fifths here. Self-driving cars. You take the Google self-driving car. How does that work? Well, it's got this little funny thing on the top of the car, also the ones you'll see that Uber just is doing in Pittsburgh, that's a LiDAR, a laser rangefinder. And it spins around, and it just develops a digital set of where everything is in the world. The computers that are driving the car then drive through that virtual world, much as you do. Now you think about the Large Hadron Collider. Well, I mean, this is the most amazing scientific instrument humanity has ever created, and they have these, and I mean, there's as big as this room, detectors, and they collide these protons at enormous energies, and all of these events happen, particle events. The rods and cones, the pattern recognition computers that are the first to get hit with this flow are being hit at about 600 million events per second. Now, what goes out to the scientist is about 100 or 200 events per second that have been selected as the ones that might be interesting. You know, you might get a Nobel Prize if you actually.
So this is data triage again.
So it's data triage, exactly as you said in the last session. But the point is that the vast computer architecture that's been built to handle these data flows has, again, just like the biological computer, a set of specialized processors that can reduce 300 million to 1 in every second, right? I mean, it's looking at all 600 million and rejecting all but 1 or 200. That's serious high-performance pattern recognition.
Yeah.
And then those data, so still a couple of hundred a second, are going out to probably 20 or 30,000 researchers all over the world who then are working on it. And that's all going over our pattern recognition computer as the LSST we're working on. So I think generally, I conclude from this that where we're going is a distributed computer architecture that has specialized pattern recognition flow computers that do what you got to do. There's too much stuff, right, in the world. And by the way, financial flows that we heard last night about, I mean, you look at the high-frequency traders, they're doing the same thing. They're looking for, every flow of hundreds of thousands of financial instruments worldwide that are going actually, many per second, which of those are you going to look at?
To put this into a bit of historic context, which is what Bill Janeway is so good at.
Yeah.
You go back a few decades and you go, well, NCR, the kind of a small or big machine.
Right.
The whole job was today's cash flow. You've got a drugstore and you want to know how many dollars.
Right.
That's a pretty simple problem. And to go from that kind of tech, which is essentially the tech we still have today, to and that kind of problem, the day's receipts, to what you're describing, it's almost like, I think it's unfair. It's an unfair requirement. So we have just changed the demand, the request from here are all the toothpaste things I sold today,
right,
to which is a linear problem really, to here is the world cut both in time slices that are increasingly small and in
resolution.
Yeah, resolution. And we want a computer or some computers to handle that.
Well, Mark, I just gave the 30th anniversary for NCSA. So I started that supercomputer center 30 years ago, just like a week or two ago. And I reflected on it from when I had done my first, my PhD thesis on putting Einstein's equations of general relativity on the supercomputers and colliding two black holes and calculating for the first time the gravitational waves that came off of them. That was 40 years ago, and last year we finally observed that. Well, that was a Seymour Cray designed supercomputer before he formed Cray Research, called the CDC 6600. It was the fastest computer in the world. And now, 9 years from now, President Obama has an executive order for the United States that says we will build a so-called exascale computer by 2025. That's 1 million teraflops per second. And I reflected on that. That's 50 years, and that's 1 trillion-fold increase in computing power.
Yeah.
Now, never in the history of life on this planet, much less the history of humanity, have you had a trillion-fold change. That, oddly enough, we need that.
And yet, even the phrasing of the president's request seems to me antiquated.
Yeah.
Because it's like saying clock speed. And in fact, we know now that it's the entire architecture that has to change.
Well, what's really interesting is if you read the executive order for the National Strategic Computing Initiative, which came out last summer from the White House, there's a kind of a ringer in there that I don't hear people talk about. And it says, oh, and by the way, this exascale computer has to be as good at data analytics and pattern recognition as it is at high-performance computing.
Oh, good.
Now, there is no supercomputer today that can do that, because it's all on Hadoop, on clusters in the cloud and all this sort of stuff. So I think actually what that is saying, and then a number of really, some of the most prominent people in high-performance computing have noticed that we are going to have to integrate like a right brain pattern recognition and a left brain logic arithmetic kind of thing, even though that's not really true, but I mean, it's sort of metaphorically true, into our supercomputers. And that's new. And I think it's because what you're seeing is this rise of data flows, data sciences. I mean, I'm working now almost entirely in data science, whereas in my youth, like when I was Benji's age, I was solving partial differential equations, you know, on supercomputers. And that, now we're doing both. You have so massive amount of data because your ability to describe the world is so much better.
Mm-hmm. And I know you wanted to talk about the industrial internet?
Yeah.
Or whatever
I want to
call it.
talk about two things. One is the industrial internet, and what has this got to do with you? I mean, you're not going to be doing probably most of the astrophysics I talked about, or hard particle physics. General Electric has spent the last decade developing a series of white papers and then actually implementing this called the industrial internet. What that is they're putting sensors into every manufactured machine, you know, jet engines or any kind of, all of the stuff is in refineries and so forth. And they're really just doing this thing. They're reading out, you know, the state of that thing every second or something. But the point about it is we have a National Institutes of Health cancer genomics, human cancer genomics database at the San Diego Supercomputer Center. And the scientists all over the medical professionals all over the world that are doing the modern cancer genomics download something like 30 petabytes a year of data. The GE industrial internet is 10 petabytes a day.
A day.
And this is in the commercial sector, not the academic sector. And essentially what that means is because you have predictive analytics, you can begin to see before things go bad that you need to go in, make a change in something. Essentially machines in the next 5 or 10 years will never stop. They will never break. They will just run forever. Right.
Report in and get fixed.
And it's all because of being able to look across every one made, every jet engine made of this kind. That's the population, right? But then you're doing an N of 1 for each of those. And it's that combination of having what the average ought to be from the population compared to what is it for that individual.
Right.
Now imagine we talk about all of you. How many of you are wearing some sort of Fitbit or other kind of device on you? Come on, get out there. Okay, better than it used to be. When I started talking about this here. So what is this doing? So this is, let's think about data flow, okay? So this is doing your heart rate. And it's not really doing it 1 per second, but let's just assume in the next generation where you actually want to do the onboard data analytics to tell you're about to have a heart attack by looking at the changes in the pattern. Okay, let's just say 1 a second. Well, how many of these are we going to be looking at Fitbit in the cloud where all this data is going to? I don't know, 100 million people? So that's 100 million per second, and the Large Hadron Collider was 600 million per second. Not so different. Mm-hmm. So to be able to monitor the health of our population as we go in from a sick care system we have today toward an actual health care maintenance system in the future that uses the predictive analytics just like we're talking about, this is going to be totally, this is now basically routine. So what I'm amazed at is the most advanced scientific instruments on the world, the data flow numbers from that and from the mass consumer markets, the billion YouTubes downloaded a day, are similar numbers at the same time.
Mm-hmm. And I don't think, you look at the growth in data center capacity, but I don't think it's getting there.
Yeah. Well, yeah, and that's the whole point about this is the reason we have data triage is we can't store that much data, we can't compute that much data if we take the raw flows. The raw flows have exceeded the ability of the entire computer industry worldwide to cope with. So that's why you have to go to, it's not a choice.
Right.
And so how are you going to triage the data? How do you know? I didn't want that, but I want that. I guess maybe you'd have to have a flow computer.
You would, wouldn't you? And that really begs the question of pre-knowing what you want. And so I think that came up during Chris Johnson's team up here, because you're making a presumption. It's just like being a kitten who can only see stripes. If you're only asking for stripes, you won't find out that there are bars. No. And so when they call it noise removal, that noise it's like junk DNA. I don't think there's any junk DNA, by the way.
No,
not
at all.
And so if you throw away all the information on the junk DNA for the first 40 years of studying DNA, you didn't learn anything about the stuff that later you find out to be important.
Yeah, but of course that leaves things for the new graduate students to get PhDs on, so it might have been a plan.
Good thing for UCSD. Well, when you look at all this, then since we have these poor souls, we're going to have to build, and we're going to judge them, by the way.
Right.
So this is probably cogent for them. Can you kind of give a paragraph outline of what you think? We'll do it again a little bit of time. A paragraph outline for what you think they're facing in terms of what this computer is.
Yeah.
So computer system. I want to be very careful. It's not necessarily a computer. It's a system.
No.
Yeah.
What I see happening now that I've really never seen before is that there's a rise of a set of specialized architectures for computers, chips, that are designed for real-time flows that never stop and that have to sit in that flow and make decisions based on patterns. And there's a just renaissance. IBM, we heard last year from Deepindra Mota with the IBM True North, 1 million neurons and 256 million synapses on one chip in silicon. And now Lawrence Livermore, since we were here last year, got a 4x4, and they're actually saying we're building a brain-inspired supercomputer. Yeah. And now Dan Golden, who you had here last year, yep, who was the longest-serving NASA administrator, and he kind of hinted at he came out of stealth, 10 years of stealth and $100 million of patient capital on June 6th of this year with his New Edge device, which is completely asynchronous,
yeah,
no clocks.
Yeah.
I mean, totally wild. And yet, what does it first do? It does voice recognition, real-time data flows, and it's going to have a whole bunch of other things. So we're at this moment where necessity is the mother of invention, essentially, that we have to have these new ways of thinking. It can't just be von Neumann architectures, which we've lived on for 60 years. Those are important to handle a lot of the overall stuff that has to get done. But then there are these coprocessors that are very different in their architecture. And so a lot of brain power on the planet is going into that sector now.
Right. And I guess it would be a good time to mention that Larry and I put out press releases in the last day celebrating yesterday, celebrating what you all saw last year, which was an idea at the time, the best pattern recognition laboratory. It's housed inside Cal IT2 at the Qualcomm Institute.
Correct.
And Larry has put his foot to the gas on this, and there are, is it 50 people, 50 scientists? Or?
Well, you had here on the stage Professor Ken Kreutz-D'Agato. He's the director. He's spent his whole life in machine learning. And so he's got all of these students. He's probably had 50 graduate students and masters working on these different architectures. But then imagining, as he was saying last year, there are this deep belief networks you keep hearing all about. That's one of half a dozen different modes of machine learning. And all of those have to be optimized on these radical new platforms, and all of those then are available for different applications. And so that's what the lab is really doing.
It's incredible, and it's real.
Well, I don't know that we would have done it without the ride.
The little silver car?
Yeah, pretty much.
Yeah. Well, anyway, congratulations on that. That's very cool. And we keep calling it the FiRe Lab, which I love.
Cal IT2, yeah.
Cal IT2. So the FiRe Lab has now got a new laboratory inside of it. We've got 5 minutes. If there are people who have questions for Larry, there's one right there. Wait for the, does a runner have a mic?
Mic's right here.
Okay.
Awesome. Question is about, well, I wrote it down to make sure I got it. But a canonical set of parameters to deal with the signal to noise.
Yeah.
I liked the idea about the car, LiDAR scanning a digital world and then driving not through the world, but through the data.
Mm-hmm.
And then the flow of the interactions in that world turns out to be a sensor that you need to watch. And you talked about a 6 million to 1 signal to noise ratio on the Large Hadron Collider's sensor.
Mm-hmm.
So in terms of signal to noise, now I've got a flow processor, and with these domain-specific computing elements, is there a canonical set of data, a canonical set of parameters that we can look at for understanding what the sensitivities are in how to tune these?
Right.
I almost want to give them personalities, right? These agents
Yeah.
in raising the signal to noise in that data-overwhelmed world.
Yeah, I mean, you're really...
This is Nathaniel Miller, who runs the small satellite program for NASA. So
Very generous.
he has a reason to ask this question.
Sure. No, I mean, you hit it on exactly the key point, and this is what Dan Golden, you know, as I said, the CEO of New Edge and the longest-serving NASA administrator, has pointed out. It's all about getting a signal in a world of noise. And with the Large Hadron Collider, like I say, you're looking, I mean, the computer actually picks out 100 out of 600 million events per second. Now, that's not going to be the same set of parameters as the Google self-driving car, for instance. But the point is that the computers, if you, I mean, for instance, one of the things they do is they inject signals into the noise and see if you can find them. So there's ways to calibrate this. This is, for instance, the Laser Interferometer Gravity Wave Observatory, LIGO, that detected the two black hole colliding. You know, they actually inject, without telling the people who are the observers, spurious signals to make sure that they don't accidentally find something, right? So there's a whole calibration which is unique to the particular application. But I would say more than there's parameters, there's a methodology that's developing here. And I see a whole new profession basically coming around. And of course now people that are in machine learning can name their price. I mean, there's way too few people compared to the enormous market demand. But I think that's really going to be a whole new profession, essentially.
We may have
Other questions? Yeah.
There's
a microphone.
Chris. And here's, while we get the mic to Chris, we neglected to mention one very small thing.
Yes.
We were talking on that road trip about the problem of, with all the sensors that are out there, everyone talks about the IoT, the Internet of Things.
Yes.
And they kind of forget the part that matters, which is if a tree falls in the forest and no one's there to hear it,
Right.
So if you put 1 trillion sensors out there, which I think is the number you threw at me that day, there are 1 trillion streams of information flowing, or data flowing back, and no particular way, A, to get that data from A to B, and then you have to handle it. So I think we agreed that the problem isn't the Internet of Things. The real problem from a technology perspective is the opposite. It's the Internet of Flows.
Right. And in fact, you know, if you take the ubiquitous drones that our military uses, but now our firefighters are using and so forth, the real problem is that the downlink bandwidth is not anywhere, it's orders of magnitude lower than the sensors on board. So again, you have to have near sensor flow recognizers
Yeah.
to handle, because it's a system.
And data triage, you
Yeah,
got.
you have to have the data triage to get the data down to the flow level that it can go out in the world. Yeah.
Okay. I'm thinking about Bill's presentation last night.
This is Chris, who's going to be on stage this afternoon or later today, who is, in my humble opinion, the most advanced researcher in bioacoustics.
Here he
in the
goes
world.
again, right?
Yeah, yeah.
2 arms, 2
Yeah.
legs, some gray matter on my shoulders. And thinking about the presentation last night about this 3-legged stool and the profound instabilities, if you will, in the flow in that system.
Mm-hmm.
And then we're hearing about this incredible explosion of technology integrated with our minds and our interests of discovery. I'm just wondering, because I was sitting next to you last night, how do you, and can you retrofit those 2 contradictions? Because the reality of what we're in is so disturbing to the flow that you're talking about, the progress we're making, which is, I think we all agree in this room, this is essential to our future. Right? And yet,
It is our future.
Yeah, it is our future.
Yeah, we got to get it right. That's why we need a few more people working on it.
Yeah.
And so that's what we're trying to do, Mark, by getting out. Mark has an ability to get memes injected into the society in a way that this alters the course of the society in time by getting more and more people to recognize this is an important aspect, and then they start moving their brains to working on that. And I think that's what I'm trying to do in my small way with the Pattern Recognition Lab. We have to get a whole new generation of people who think this way, because the world is going to totally depend on the ability to do flow computing. End of story.
So there's a whole other layer in here of those who actually translate downstream from what you're doing, translate that, bring that into the consciousness of billions of people.
That's right.
Yeah, true. Thank you. Well, we've done it again. Thank you, Larry.
My pleasure.
Very cool.